All right, so another case where you have sufficient symmetry to use Ampere's law to solve for the magnetic field is the case of planar symmetry. And so planar symmetry implies that you have, in a Cartesian system, you have no variation in the current in two directions. So in other words, you have a sheet of current where on that sheet everything is constant. Okay, and across the sheet you can have a variation in the current density. So let's consider that case, and let's take a thick current sheet. Okay, so I'm going to take a sheet of current and I'm going to draw it with finite like a slab, but we're going to argue that the extent of the slab goes to infinity in two directions. You imagine you have some current that's flowing, and you can imagine it's a big slab of copper, for example, and there's current flowing down. The electrons in the copper are moving to provide a current. So if I look at the current on this face here, I'm going to have current into the page. We'll have a coordinate system that has, let's see, what am I going to do? We'll say this is y hat. We'll call this direction x hat. And then the current direction, which I guess I'll draw as a tilted like that, is the z hat direction. Okay, and we'll give the slab a certain thickness. We'll say that this is y equals to 0, and we have the slab goes from y to a, y of a to y of minus a, so the total thickness is 2a. Okay, all right. All right, so to have the requisite symmetry that we need, we really have to argue that in this dimension, the slab is infinite. Okay, so in the x direction, we have L of the slab, the length goes to infinity, and also we have to assume that in the z direction, it's very big too, that there's no variation along the z direction. So Lx goes to infinity, Lz is also infinitely big. Now, in reality, again, there's no infinite current sheets like that, but if you have a very big slab, you can approximately argue that the field looks the way that you would calculate, assuming it's infinite. Okay, so the first thing we start with is visualizing what the field is going to look like, and then let's try to calculate it. So if we imagine this slab of current as being made up of a bunch of wires, okay, and let's just take a single wire. It's really a fat wire, but let's ignore that for now. Okay, so if we have a single wire that's carrying current, actually let me do it this way. Let's say the wire is carrying current into the page, and there's a wire right there. We know what the magnetic field looks like of that wire, so if the current's into the page, then the magnetic field is going to loop around the wire in that way. Okay, and then it's as if you stuck another current right next to it, and here I can use different colors, so I'll do that. So here's another wire that has current into the page, and it's going to have a magnetic field that circles around like this. Okay, and if you look in this region here, you see the two magnetic fields cancel. Up here they kind of add together, down here they add. And so as you add more and more wires as you go out, the field will kind of straighten out on top here, and on bottom, let me use a third color here and try that again. So the field on top will add up and be reinforced like this, but in the middle, so in between the wires, you're going to mostly cancel out the current, the magnetic field. So the net result is if I take this slab of current. Now that argument was for a bunch of wires, but it turns out that if I take a slab of current like this, outside the slab, the same argument will apply. I'll have a magnetic field that will be, in this case, one direction on the top and the other direction on the bottom, like this. Now, if the slab is finite, the field lines will close around like this. Okay. Now, if we let the slab go to infinity, this straight field line will continue left and right forever. Okay, so this field line will go on forever. Okay. All right. Now, it's not clear yet. We can see from this right away because the field line is straight. It doesn't spread out. Going left and right, so in other words, in the x direction, the field will not vary. Okay, and that's given by symmetry. It has to be the case. The only possible variation can be vertical. So in the y direction, the field might vary. Okay, but as we'll see in a second, in fact, it does not. Okay, so that's our visualization of the field. Let's try to do an Ampere's law calculation now. And there's a couple ways to do this. We're going to specify the problem as a thick current sheet, so we're going to have some current density J inside the slab. Let me go to the next page here. All right, so let me redraw my slab of current here, which again we're imagining is infinitely big in these directions, or at least very big. And we have some current that goes into the page everywhere in this slab. So I'm just drawing it on the center line here, but this current that fills the slab, that's constant with value J, current density. Okay, so we know the field, based on the argument previously, the field here is going to be going this way on top, and on bottom going this way. Okay, so we're going to pick an Amperian loop. And again, this is completely up to us. We're going to exploit this symmetry of the problem. We need to pick a loop and a surface that is bounded by that loop, such that the loop, everywhere on the loop, the inner b dot tangent of that loop is constant. Okay, and so we just argued that the magnetic field does not vary as we move in the x direction, which is that away. And so if we pick a line that follows along the magnetic field like this, okay, and goes in that direction, this is a case where b dot tangent of that line is always constant, and we can pull it out of the integral. So we need to close this and make it into a loop, and we can do that by going straight down and then across and then back up again. Okay. And so down here on the bottom, you also have the situation that the magnetic field is along the direction of dl, and it's constant because it's not varying as we move left and right. And then here on these side loops, the b dot dl is 0 because the magnetic field we know can only point right or left based on symmetry. And so inside here, these two legs give you no contribution. Okay. Now I'm going to pick my loop so that it's symmetric about the center. So if this is the center of my current sheet, I'm going to call this distance y, and this distance will also be y. Okay, so really this will be at position y, this will be at negative y. Okay, if we call this y equal to 0 here. Okay. Now, by symmetry, the strength of the field at these two locations has to be the same. Now, the direction is opposite, but the strength has to be the same because there should be no reason why the strength would be different on one side of the sheet and the other side of the sheet at the same location, okay? Because everything looks the same, it just the directions are reversed and that's it. So we know that the strength of the field here, B at y, is the same as B at minus y. Okay, not the direction, but the strength. All right, so if that's true, then I can write down my integral of b dot dl. Okay, in both cases, b dot dl is positive, okay, because dl goes to the right on the top and to the left on the bottom. So if I do b dot dl, I get a positive number for both. So this becomes 2b, okay, at the location y, okay, or minus y. Times the length, okay, of this line. And the length I'm talking about is this length here, okay? All right, now we need to calculate mu naught I enclosed. And so what if I look at this Amperian loop, the current enclosed is the current in this green hatched region that I'm just drawing here, okay? So there's no current out in the region that's over here, okay? No current here. So what matters is the area of this rectangle, okay? Now if I had J that was non-constant, I would just integrate over this area. But now since J is constant, I know the integral of J dot dA is just J times A. And the area that matters again is just this green hatched area because that's the only place where current exists. And so in that case I know that the integral of J dot dA is just going to be J times length times the the extent vertically of that green rectangle, which is 2a. Okay, and so if I do integral of integral of b dot dl equals mu naught j integral of j dot dA, so that's going to be, let me just write it so I'm not losing you here. Integral of b dot dl. This is a statement of Ampere's law. Okay, that's what we're trying to evaluate. This is going to be 2bl. Okay, and let me just be clear. This is b at position y above the current sheet times L is mu naught times J times L times 2a. Okay, and so what you find is b at that location y, or minus y, okay, is mu naught J A. Okay, it's constant. All right, so the magnetic field is independent of that distance y. This is, again, the calculation I'm doing right now is specifically for y bigger than a, so it's outside of the current sheet. Okay, and so for any value y, which is bigger than a, I find the same value for the magnetic field, because I didn't specify, this is not particular to any y. I'm allowing it to be any value above a, and I find that it's constant. So the magnetic field is constant. This is very much like the electric field of a charged sheet, an infinitely big charged sheet. It's uniform everywhere in space. And you can argue the same kind of thing about it. So for each little bit of current, imagine this is a bunch of wires that you're adding up to make this slab. So each wire has a 1 over r field that is contributing to the total field. But because you have so many wires going in the x direction, extending out for forever, if we really truly have it infinite, those wires, the field from all those wires add up in a way to keep the magnetic field uniform everywhere in space. Okay, and so the way to think about that is as I step away. So as you're close to the sheet, you see only a few wires, but as you start to step away, you look to the left and the right, and there's, you see a bigger and bigger amount of wires, I guess, going off into the distance, and you kind of prop up the field as you go out. Okay, and so the field remains uniform all the way out to infinity if the sheet is infinitely big. Okay. Now, if the sheet is not infinitely big, that will only be true. Oops, let me get rid of that. If the sheet is not infinitely big, that will only be approximately true. Okay, and the way that we test the goodness of our approximation is we can argue that if y is much smaller than the length of the sheet in the x direction, we should expect our solution to be good. Okay, so our infinite solution should work pretty well. If y is, approaching the value of the size of the sheet, so in other words, I have a sheet like this, and I'm kind of looking right there, so that this distance and this distance are about the same. We know that it's going to see this, quote, see these edges over here, and the field is going to, the real field will look like this, and it's going to start to spread out and get weaker as you go further away. And in fact, as you get far enough away, this sheet will look just like a wire eventually. Okay, you're not going to notice that it has an extent in the left and right direction. And so as you go further and further away, this is going to look more like a 1 over r field. But as you go closer and closer to the sheet, it'll look like a uniform constant field. Okay. All right. So we did the calculation for y bigger than a. Let's consider now y less than a. And if I look at my slab here, I should make it bigger. Make my slab bigger here. I'm going to pick an Amperian loop now that is inside, like this. Okay, but the same exact kind of loop. And I'm going to pick it again so that I go a distance y on either side of the center. Okay, so that this distance is y. Oops, and this distance is also y. And I make the exact same argument as before, that the field inside has to be symmetric. In other words, the same magnitude at above and below, but reversing directions. Okay, so I'm going to assert that the integral of b dot dl is the same. It's 2 times b at location y times L. Okay. Now, when I write this, I'm acknowledging that this is the magnitude of the field, and the direction is reversing. So the direction is already specified. The direction is to the right above and to the left below. Okay. And this is, I'm solving for the magnitude at that location, a distance y away. Okay, and then this is going to be equal to mu naught times the current enclosed. And in this case, I'm doing the same thing as before, but now the current that's enclosed is here, and it's not the whole slab. It's part of it. So it's going to be J times L, the same L here that I'm using here, and then I'm going to have 2y. Okay, that's the length of this this side. Okay, and so now I find that the magnetic field is not constant with y because I'm enclosing more and more current as I go out. So I get mu naught Jy. So the field is increasing linearly as I move away from the center, and I find the field has to be 0 at the very center of the sheet. Okay. All right. And so if I plot that, I'm going to have, let me do it this way. This is Bx versus y, and what I find, give myself some more room here. There we go. Okay. What I find is that the field, when I'm inside the current sheet, so here's minus A, and here's plus A, it's 0. Let me pick a different color here. 0 on the axis. It increases linearly and decreases linearly like that, okay, away from the origin, from the center of the sheet, and then it becomes constant on the outside. Okay, constant positive on one side and constant negative on the other side, so it just reverses direction. Okay, so this is the field of a thin sheet, a thick sheet. Okay, and you can imagine that if I make this sheet very thin, the answer is going to be that it goes from a value that's plus on one side to a value that's minus on the other side. This is if I let A go to 0. Okay, so B, this is like an infinitely thin sheet of current. You get a jump in the magnetic field, okay, as you go, that's supposed to be the y-axis here. You go from one side to the other, you get a jump in the magnetic field due to that thin current sheet, okay? All right, so I'll stop there and I'll do another example problem on the toroidal magnetic field next, which I know you're all excited about.